Hi, and welcome to this video where I am going to implement what is called the John Conway's Game of Life, which is a cellular automata rule for evolving grids of two-dimensional objects in a way that it feels like they are tiny cells that are alive or dead and they're reproducing and popping out. And if I may show you a demo of the thing working right now, I can activate the simulation and you can see how from an initial state there is this kind of like situation of cells looking at each other and reproducing and popping up and down. I think it's a really cool thing. Um, and I'm going to do it in two parts. This first part that you're watching at is a part where I'm going to do some certain simplifications for the sake of speeding up the process. So I'm going to take data, I'm going to oversimplify that data to make the process a bit faster. And then, so what you will learn in this video will be to use two-dimensional arrays and to use this technique where we can use persistent data in a C# component to to um, to be able to use that data over iterations of calculations. In the second video, what I will teach you is to do the exact same thing, but instead of simplifying the data using data trees natively, and therefore be making the code a bit cleaner uh, and more compatible with the general ecosystem of Grasshopper. Did you guys see that crash that just happened right there, and how like this is going to blow out? How cool is this? Okay, so stay with me, and this is a bit of an advanced tutorial. So if you're not very familiar with C# yet, I would like to recommend you to check my C# tutorials that I have not yet recorded, but whenever I do, they will show up on the video description, on a card, somewhere here, etc., etc. Okay, but stay with me. This is going to be a lot of fun. Okay. So, what is Game of Life? As I said before, Game of Life is this form of cellular automata that Professor John Conway came up with, which has been very popular in recreational mathematics and in like sort of like basic life-like evolutionary simulations, etc. In which basically the idea is that there's a basic structure of two-dimensional grid of cells. Some of them, and they can only be alive or they can only be dead. And then there are some rules about how each step of the simulation, how those cells evolve, and how some of them live and some of those die. The nice thing about Game of Life is that the rules are tweaked in a way that it gives you a very strong impression of this kind of like lifelike elements, like populating and replicating and dying over time. You know. So, for example, I'm using this online Game of Life simulator at copy.sh, which I initialize with a random sample. So this basically looks like noise. But if I run it, you will see that as soon as the Game of Life rules start kicking in, we start getting this like appreciation of like these like elements that are alive and are moving around and are reproducing and are dying over time, etc. So it's a really interesting and really playful thing to see and to work with. So this is where we're going to try to mimic something like this today. And before we go into actually making any code, I want to do what is best before designing any kind of algorithm, which is talking about breaking down the rules of how this actually works at a low level. Okay, so for that I'm going to use some diagrams. So let's switch to the whiteboard. Good. So we are back on whiteboard mode, and I drew this two-dimensional grid of cells. All right. And as I was saying before, the Game of Life is based on the idea that each cell can only have two states. It can only be alive or it can only be dead. And it also is based on the idea that we start from an initial condition. So if we start from all dead, all cells being dead, very likely nothing is going to populate. All right, unless we tweak the rules, but I'll get to that at the very end of the stream. But let's start with an initial situation. Okay, so what I'm going to do is I'm going to randomly or purposefully, it doesn't really matter. I'm going to say, for example, this cell is going to start alive. This cell is also going to start alive. This cell is also going to start alive, and this one, for example. Okay, those are the 5 cells that are our initial condition and then start as alive, okay? And I've done a trick here. I've actually drawn a glider. I think this is called a glider, which is a really well-known form for the game of life, but which kind of like self-replicates and keeps and maintains itself eternal. But you can Google that, or you will see it working later on. But anyway, it's a good example to start. The idea is that think of this as iteration 1. This is the first step of our simulation of life through the game of life, right? The way the rules work about how cells evolve over time is very simple. There are two situations that can happen. A cell can get born, or a cell can survive. Otherwise, everything else is cells die, all right? And there are two very simple rules about that. A cell that is alive will survive if and only if it has 2 neighbors or 3 neighbors that are alive. Again, this is for the John Conway's basic standard game of life. And at the same time, the rules for how a cell gets born are that a cell will only become alive if and only if 3 neighbors around it are alive. Okay? So let me show how that works here. Let's take, for example, I'm going to create a new layer. I'm going to create a new color here, and green is going to be the second iteration. Okay? So we're going to look at this cell here. All right? The one that I have here. And for this cell, we said I'm going to write down the rules. A cell is born if 3 neighbors are alive. All right? And a cell survives if 2 or 3 neighbors are alive. Otherwise, all cells die. Okay? So let me go back to that. This is called the B3S23 rule, and those can be changed and can be customized. It just happens that it is well known that for this particular rule, all these like nice patterns, evolutionary patterns arise. So, for example, let's say that we have this cell here, this one that I'm going to color as green. This one was alive in the previous iteration, so it will remain alive this iteration because this, can you see my screen? Because the one on the left is alive and because the one on the bottom is alive. So it has 2 neighbors that are alive, which means that it sticks to the 2 rule. Now, will this cell stay alive? It will stay alive because it has 2 neighbors that are alive. Will the one on the left stay alive? So this one, I can't point it here. So this one, where is my mouse? Where is my mouse? Oh, here. So will this one remain alive? It will not remain alive. So this one here. It will not remain alive because it only has 1 neighbor that is alive. So that one is going to die on the next one. What about this one here? Is this one staying alive or is dying? This one is staying alive because it has 3 neighbors that are alive. This one, and this one. All right? And actually, before I made a mistake, this one stays alive because it has 3 neighbors. It has this one, and this one. All right? Now, what about this one here? Does it stay alive? That one dies because it only has 1 neighbor next to it. Okay? And what about the ones that get born? The ones that get born are going to be the ones that have 3 neighbors that are alive. So that one is going to be this one here because it has this one, and this one, right? It's going to be which one else is going to be? It's going to be this one because it has this and this and this, right? And which one is it going to be? So this one, you see this one here, that one has 5 neighbors, so it's too much, it's suffocated, so it doesn't stay alive. Okay? I might be getting this wrong, but you guys get the message. Okay? So I think this, as far as I can tell, this will be the next iteration, because this one, for example, only has 1 neighbor. This one only has one neighbor, one neighbor. This one has two neighbors, so it doesn't get a life. Two neighbors, no. Two neighbors, no. Two neighbors, this is only the one. Okay, so this would be the next iteration. So if I now hide this layer, this would be iteration 2 of the game of life. Now let's take a look at iteration 3. Now if I change colors and I create a new layer, you can see that, for example, this cell is going to die because this one is going to stay alive because it has two neighbors, this one and this one. This one here, what is going to happen to this one? It has four neighbors, so this one is going to die. This one has one neighbor, that's going to die. This one has two neighbors, that one is going to remain alive. And this one has three neighbors, so it's going to remain alive. And what about the ones that are going to get born? This one is going to get born because it has these three neighbors alive from the previous iteration. This one is going to get, oh no, not that one, sorry. Which one? This one is going to get alive because it has these three neighbors. And what else? I don't know if any other is going to go alive. But this would be the third iteration of the game of life. So let's, I'm probably not getting this right, but let's assume that that's the case, okay? So I'm going to remove this, I'm going to remove the previous iteration, and then for the last iteration, I could say, well, for this one, now, I don't know if you guys noticed, but I already have, remember the glider that I told you about? This is the same shape, it just has been rotated and moved a little bit. So now we're basically starting again with a similar situation where for the next iteration, this one is going to be born, this one is going to remain alive, this one is going to die, this one is going to remain alive, this one is going to remain alive, this one is going to die on the left, and there should be another one popping up. This one is going to pop up because it has three neighbors, right? So, and as if you notice, oh, I should have done red. That would have been, it's okay. But you notice how now, yeah. So, and then our evolutionary game would be something like this. We start here, next iteration, next iteration, next iteration, etc., etc., etc. All right? So these very, very simple rules, the idea of how cells survive depending on their neighbors and how cells get born depending on their neighbors is a very simple rule, but as it evolves over time, it creates this like emergence of complexity that is really interesting and really playful. Turns out that it's not very difficult to write this algorithm, so that's what we're going to do today. So let's get hands-on. Great. In order to implement these rules and this algorithm in some kind of simulation, we're going to use Rhino and Grasshopper, and we're going to implement this by writing a custom C# script component where we're going to implement all these rules. So the first thing that I want to do in order to get there is I want to create something that looks like a grid of cells, and I want to create an initial state where some of those cells are alive and some of those are dead. So for that, I'm just going to use plain vanilla Grasshopper. I'm going to create a rectangular grid of points, and I'm going to use some logic to figure out which ones I'm going to consider alive and which ones I'm going to consider dead, which I'm probably just going to draw like some curve on Rhino and use like curve containment and something simple, like something fast. So let's do that real quick. So I'm going to use bifocals so that I am sure that everybody can see icons, but they can also see the groups and the tooltips on top of the names of the components. Now, what I'm going to do is I'm going to create a grid, a rectangular. It's going to be a square grid of points because I don't want distances to be, and that's going to be the base plane. The size of the grid is going to be 1. It doesn't matter. And for example, for this, I'm going to for how many elements in each direction there are. I'm going to keep these two separate ones just because I want to be able to debug. So let's say I'm going to do 50 by 30, for example. Okay, so I got a grid of cells. For example, 50 by 30 or 40 or something. I have a grid of cells. I have the actual cells, but I also have points. So I have the points here, for example. So, and what I'm going to do is I'm just going to draw like a curve here, like a small one. I'm going to bring this in here. All right, and then I'm going to use curve containment to figure out which of these points are inside the curve and which ones are not. And those are going to be the ones that are going to start as alive. I could also implement some kind of randomness, but I think this is just an easy way to start. So for example, are these points inside of this curve? I'm going to get results from 0. Let's plug in a panel here. So the results are 0s, 1s, or 2s. And if you remember, 0 meant outside, 1 was coincident, and 2 was inside. So I'm going to check if these values are equal to the number 2, because what I want is I want to end up with a list that tells me whether if elements are inside or outside. So false, 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 and then you see I hear some truths here. Those are the ones that are going to be inside of the curve. And I could, just for visual purposes, I could just call these points here by the pattern. All right, so that I can see that correctly. This is indeed the first point that I'm going to start with. Okay, so this is important because what I want to feed my component is not going to be the list of points. It's going to be the list of truths and falses, so that I can play with those as the states of my cells. Okay, so so now that we have a basic scaffolding for this, I'm going to start writing we're going to start writing the C# component. Let's get to it. A C# component where I'm going to take the cells, and I'm going to take them as I'm going to take them as a list, and here I'm going to tell how many cells are in the x direction. No, how many rows are in, and how many columns, because I want to know the size of the grid, because something, and this is important because, let me explain this first. What's coming out of here, when I created my grid of points, you can see that what I'm getting is a tree that has 51 branches, and each one of those branches has 41 elements. Okay, so it's important that we could work with this data tree of elements, but I want to simplify this first and flatten those as just like one single, instead of this data tree structure, I just want one single list with all the elements one after the other, because that's going to make my life a little easier inside of the C# component. Okay, that's going to be part 1. I'm going to do that simplification, and then in part 2 I will work directly with the data tree structure. So the cells that I'm going to take are going to be, this is going to be a list of truths, Boolean values, truths and falses, and then rows is going to be an integer. So it's going to be an integer because it's the number of rows that my grid has, and the columns is also going to be the number of rows that my grid has. I'm going to add a couple of other inputs. I'm going to say, should we run this simulation? And for this, I'm going to use a Boolean. And I'm also going to say, should we reset the simulation? Should we start from scratch? And for this is also going to be a Boolean. Okay. So with this, if I plug this in here, I think we're ready to go. I will need to plug the number of rows, and that's going to be the number of elements in the x direction plus 1, and that's also going to be, for the columns, is going to be also the number of elements plus 1. So this is the number of rows. So, and this one is the number of columns, if I am correct, right? Yeah, 41, 51, and if I look at the data, you see that I have 51 branches with 41 elements, so we're good. 41 is going to be the rows, and the other one, actually, it's the other way around. Yes, so I'm just going to do the other way. Yes, I'm gonna keep it that way. Maybe I change it in a second. Okay. All right. Now I'm just gonna change it. So rows are going to be. No, I'm gonna keep it. Columns are going to be branches, and rows are going to be elements within each one of the branches. Okay. And then here I'm just gonna plug in some toggles. So Boolean toggle for running and Boolean toggle for resetting. And with this, I think we should be good to start writing the component. Okay, let's get to it. Let me save this as usual. I'm just gonna save it somewhere here. Game of life 1. And this is going to be game of life 1. Oh, game of life 1. Okay. And let's get to it. Okay, let's get to it. I'm going to go into my C# script component, and I'm going to open my script. And then here you can see that I have a list of objects called cells. I'm actually going to I have to take a look at this because I need them to be Boolean values. So I'm going to right click here, type hint, these have to be Boolean values. All right. I'm going to double click, and I'm going to see that I have a list of cells. Okay, and then how many rows I have, how many columns I have, and whether if I should be running or resetting. Okay, so I'm going to start very simple, just with some sanity. So let's make sure that if we are running, we should be, so if run is not true, so if run equals false, then just don't do anything, return. Okay, now the next thing that I would like to do is I will work with the reset later. But the first thing that we need to do is we need to take the cells that are coming as a single list, and we need to create a 2-dimensional array to take a look at, to make our life easier when we are checking for neighbors. Okay. So what I'm going to do is I'm going to write a simple algorithm to take a list that is like all the elements one after the other, and to turn that into a 2-dimensional array. So the first thing I'm going to do is I'm going to say I'm going to create a 2-dimensional array of Boolean values. Okay, and this I'm going to call this new cells, the new state of the cells. Okay, and this is going to be equal to a new Boolean array of what am I doing? A new Boolean array of how many columns are in the and how many rows. Okay, I'm going to see. Okay, we already have. Okay, invalid rank specifier, blah blah blah. Okay, I think this is probably because I'm not defining the double. Well, this is also, there's also a typo here because I'm probably not defining correctly my 2-dimensional array. So let me take a look at that because I haven't done 2-dimensional arrays in a while. Okay. C# two-dimensional arrays. How do you do multi-dimensional arrays? Blah, blah, blah. Okay, so, all right. So yeah, so I was doing it the JavaScript way, I think. So I guess we're going to do it this way. Yeah, so instead of having two square brackets as the multi-dimension, I think this comes from Java, actually. I think the way that is done in C# is by specifying this comma between and then specifying the two dimensions inside of the bracket. Okay, declaration. So let me do that. I think the error that we're hitting here is that instead of that I wrote two empty declarations for the array, and I believe that in C# you actually do double two-dimensional arrays by specifying that there has to be a dimension separator within the array, something like this. Okay, so if we do this, we can see that the array now has two dimensions, how many columns and how many rows. Okay, so I'm gonna add a comment here, turn the list into a 2D array. All right, good. And now what I'm going to do is I'm going to take all these elements and I'm going to put them inside of the double array. So how is that going to work? What I'm going to do is I'm going to write a double for loop where I'm going to say j is going to be equal to the number of columns, and then inside of this for is going to be yi is going to be equal to the number of rows, I plus plus. All right, and here I'm going to be going over each one of these elements and adding it to the array. However, I know that I and j are going to be iterators for rows and columns. So, but I need to know from this how many, which is the element that I need to take from the long list of cells. So there are two ways I can do that. I can either use I and j and work with those numbers to figure out which one of the elements is on the list, or just keep an external iterator, for example, it that is going to start at 0. And every time we pick one element, we use this number and we update it by 1. Okay? Also, some sanity that we should do is if the number of cells is different than rows times columns, then we should give some error to the user, like component dot add runtime warning, Grasshopper runtime message level, the error, like something weird with dimensions of the grid. Okay, and return. Okay, so we got this. This is working. I have a typo somewhere. In line 70, columns. Okay. All right. So, and this is the value iterator is assigned but never used. Okay. So let's keep going. So, and let's see if this works. Because like now, if I were to plug, for example, this directly, it would have to give me the error. Oh, it doesn't give me the error. That is very strange. Okay, so maybe, or maybe because of this thing is not properly working. Okay, so maybe, how is this not changing anything? Okay, that is very strange. Let me pause here and figure this out because this is kind of strange. So if the number of rows and the number of is not the same as how many elements, this should be giving me a, is this executing properly? End of script. Oh, because I'm not running. Okay, yes. All right. Okay, and now if I plug this here, okay, yes. So now we get the error, then something weird with the dimensions. Okay, run toggle is set to false. Yes, you're right. Thank you. All right. Yeah, these things are a lot of this is going to happen very often. Okay, let me get back to that. Okay. Um, Yeah, the problem was that my toggle for running was off, so that's why there was no calculation being performed. But as I do this now, you can see that we get the error. Something weird with the dimensions of the grid? Yes. So we are good to go now. Okay, let's keep going. So we have an iterator here, and something that we can do is we can say, well, for every, what we're going to do is we're going to say, um, the new cells with and since we're doing columns here, this should be J, and since we're doing rows on the second dimension, this should be I. This element is going to be whichever one we found on the cells list. So cells it, because we start with 0, and then for every iteration of the for loop, we update this count by 1, so that we're going sequentially by each one of the elements on the int list. All right. Let me run this, and let me just output the value of the new cells, just in case, to take a look at what it looks like outside of Grasshopper. So if I do that, and if I output this, you can see that I have this structure where it's all the elements one after the other, and you can see that Grasshopper doesn't take two-dimensional arrays. It doesn't really turn them into a data tree structure automatically. We will have to do that ourselves. But that's what I was talking about before. That takes a bit more time. So I want to get the actual algorithm running first, and then we can take a look at like better ways of working with the data structure. Okay. Okay. So here, new cells. I don't like this name. I'm going to say cell array. I'm going to call this the cell array. And the next thing that we want to do is we want to now write something that takes this array of cells with rows and columns and with the values of true and false. And then we start iterating and taking a look at how we can generate the next iteration of these cells by applying Conway's game of life rules. Okay, so let's take a look at that. Before we go into writing any code, there is something that we need to add to the component as an input. And if you remember, when I was talking about how the game of life rules work, I wrote here this section where I broke down that for a cell to go from death to alive, it needs to have 3 neighbors, and for a cell that's alive, to stay alive, it needs to have either 2 or 3 neighbors. Those are the numerical rules of the standard game of life designed by Conway. But those numbers could change. You can come up with your own numbers. It just so happens that this particular combination is known to give very nice visual results, but you could choose another one. And that's because we're writing the algorithm. We want the parametric power to like choose those rules, right? So I would not want to hard code these numbers. I would like to have them as inputs to my component so that in the future, you guys can play with different combinations of the rules. You can go online and look at, there's like tons of people proposing their own combinations of rules and how that works. So you may want to tinker with that. So for that reason, we're going to input these values, the rules of the evolution of the cellular automata, as numbers, as inputs of the component. So let's do that. I'm going to go back to my script. And then what I'm going to do here is I'm going to add a couple more inputs. So I'm going to call this birth rate, birth rules, for example, and I'm going to call this survival rule. Okay, and these are going to be, both are going to be integers. They're going to be the number of the number of neighbors that they need. But, and remember, something that I'm going to do, instead of keeping those as single items, I'm going to make them lists, because you may want to add 2 or 3 numbers to the survival rate, or you may want to add more numbers to the birth rate, right? So that's why I want to go back here and say that the birth rule must be a list access, and that survival rule must also have a list access. Okay. 120. I don't know what's going on here. Okay. Let me take a look at what is going on here. Why is this going red? Okay. Yes. So we're trying to output. Of an array. Okay. Huh? All right, that worked. Okay. Let's get to it. And now that we have our birth rule and our survival rules as lists, I'm just going to input here, for example, I'm just going to input here the number 2 as the birth rule. I'm going to do like multi-line so that I may want to add more elements later. And I'm going to copy paste this, and I'm going to say the survival rate is going to be 2 and 3. And that's going to be also a list of elements. Okay. All right. So let's get back into the component and start writing those rules. So here, what I want to do is I want to create a new array where I'm going to define which one is the new true and false pattern for being alive or being dead. So new array of alive dead cells for next iteration. Okay, so here I'm going to say, for example, I'm going to copy this boolean new cells is going to be columns and it's going to be rows. It's going to have the same dimensions, and then this I'm going to change it a little bit. Okay, now that I have my double for loop, what I need to do is inside of each one of these for loops, I need to calculate for this one cell that I'm in. So for example, bool current state is going to be equal to cell array, so where we were before, and then this is going to be j and this is going to be I, because j is for columns and rows is for and I is for rows. So this value tells me where I'm going to call this previous state actually. Okay, I'm going to call this previous state. The next thing that I want to do is I want to calculate how many neighbors are alive. Okay, so for example, I can start a variable here called alive neighbors, and I'm going to initialize this to 0. Okay, because I don't know how many I have. I'm going to add here compute alive neighbors, for example. I start this with 0, and then I think this is where it's going to get a little lengthy. I'm going to write a lot of code that could probably be optimized, but I just want to make sure that we understand what we're doing. Okay, so let me go back to the whiteboard and diagram this situation. Okay, let's analyze what we're doing numerically on this 2-dimensional grid with a diagram. Okay, so let's imagine we are on this cell here. I cannot draw. Let's imagine we are on this cell here, okay? And as we said before, we have a convention where we're saying these are the number of columns, and this direction is the number of rows, okay? Columns, we're representing it with the letter J, and columns, we're representing it with the letter I. You can see that this cell right now is 0, 1, 2, 3, 4, 5 is J equals 5, and 0, 1, this cell is row 1. So this cell is going to be 5, 1. Okay? That's I and J. Now what we need to do is, if this cell is currently on J, I position, what we need to do is we need to check the 8 neighbors that are around. So for example, the top left, the top right, the left, the right, the bottom left, the bottom, and the bottom right. We're going to check each one of them to see if they are alive or not, and we're going to keep counting. And the way we're going to do that is because we know that each cell has a coordinate of J and Y in the two-dimensional array. We also know that the top left one is going to have, so for example, this one is going to be J minus 1, I plus 1, right? This element here, this neighbor here, would be, for example, the same J that the cell has, but I minus 1, you know? So we're going to do a lot of that, but also at the same time, we need to figure out special situations as, for example, imagine that the cell is here at the boundary and there are no top neighbors, so we need to address that situation as well. The way we would do that is by, we could assume that if there are no neighbors, then they're all dead. We could simulate that. Or we could say, we could implement like a wrapping condition where we say, well, if there are no top neighbors, let's assume that these guys here are going to be the top neighbors. So that whatever happens keeps happening, like keeps wrapping up from one dimension to the other. I think that is a really cool. I think we're probably going to do the wrapping part because it's just cooler and it will make the simulation keep alive for longer, I think. So let's go back to code. Cool. Let's figure out how many neighbors do we have here. So as I said, we need to first, for each one of the neighbors, we need to figure out which one is the row in which they are and the column in which they are. So for that, I'm going to create these two variables. I'm going to create a variable called ni, so new I, and so neighbor I and neighbor j. And I'm going to use those to like figure out for each one of the 8 neighbors which one of their number along the count and the column they should be. All right. So how is that going to work? Let's start, for example, with the top left. The top left element is going to be for ny is going to be, as we said in the diagram. Top left is going to be in terms of I is going to be 1 unit less, yet 1 unit more. So that's going to be whatever we are, which is I, plus 1. Okay? And then nj is going to be the opposite. Whatever we are in j minus 1. And now here, what we need to do is we need to check if, as I discussed before, we need to check if that neighbor might be outside of the range of the array. So the way I'm going to do that is by saying, and if it is outside of the array, then we need to wrap. We need to go to the other side. Okay. So for example, if for this element, it turns out that the new I is greater than the dimension of the array, we will make I equal to 0 so that we wrap down here. Okay. So let's do that. So I'm going to, for this one, I'm going to compute if ni is greater than rows minus 1, then ny should be equal to 0. Otherwise, if ni is less than 0, then ni should be, I'm going to write else if, and if ny is less than 0, then ny should be equal to rows minus 1. Okay, so that is the last element on the row. Similarly, if nj is greater than columns minus 1 and j equals 0. Otherwise, else if nj is less than 0, then nj should be equal to columns minus 1. Okay? As we do this, now we can check. Now that we know exactly what is the position of ni and nj, so what is the position of the neighbor, then what we can do is we can say if that neighbor is alive, then we should add one more to the count of how many neighbors are alive, which is alive neighbors here. So I'm going to say here if cell array. Okay, so if cell array, that is where we were before, nj and I equals true, if that was alive, then alive neighbors should be incremented by 1 unit. Okay, let me run this. It looks like there's no errors. I'm not sure if this is going to work. I just hope it does. But yes, so you see how we had to write 7 lines of code just for this one neighbor. I think this is a little simpler to read, but yes, we're gonna have to do this for the other 7 neighbors, which is gonna take some time, but I just think it's a little easier to read and easier to understand. There are ways to make this a bit more optimal, to write a rule to go over the 8 neighbors at once with for loops, but it's a bit more complicated and I don't want to get into that level of complexity yet. Okay, so what I'm going to do is I'm going to write all these rules for the top, blah blah blah. So, and I'm going to do it like real quick. So if you know what you're doing, you're welcome to skip a little bit of this video. Otherwise, just follow with me. I'm just going to do it like real quick right now. Okay, let's get to it. So for the top, I'm just gonna copy and paste all of this. And remember, copy pasting is your enemy, is your neighbor. It's not, sorry, not your neighbor, your enemy. But for the top part, if we look at the diagram again, we see that if this is the one where we are, for the top one here, I needs to be incremented by 1, but j should be the same. So if we go back here, we are, where is my mouse? I plus 1 is good, and j should be the same, and everything else is just the exact same thing. So I'm just going to copy top, and I'm going to do top right. And if you can see from this rule, you can see that now I is still I plus 1, but j should also be j plus 1, because we're moving in this direction. Okay, so j plus 1 for the top right. Now, if I copy this and I stick to left, we can see from the diagram that on the left, j here will be minus 1, but I, the rows, stay the same. So I stays the same and j is j minus 1. Now I'm going to do right, and the right is going to be the exact opposite. So I'm going to do I stays the same, j becomes j plus 1. Now bottom left. What is bottom left going to look like? Bottom left is going to say I is going to be negative in this case, is 1 less. Oh, I'm not on the right screen here. So bottom left is I minus 1, and then j minus 1 as well. So now we can do bottom, and for bottom you can see that j is going to be the same because we are on the same column, but I still remains minus 1. So we're going to do that. I minus 1 and j equals 0, equals the same. And then bottom left, bottom right is going to be j plus 1 and I minus 1. Okay? And this was a lot. So let me just print here alive neighbors is going to be equal to this thing we just calculated to get a sense of whether if we are if this might make sense or if we are tremendously wrong. Okay, so here we're going to print this to the console, and as we do, we can see that, for example, we have, let's match these two lists here. So let's make this list here, and let's look for the ones that are around 1000 something something and see how many neighbors they have. 1028. Ooh, we might be onto something here, because as you can see, from 26 to 33, 26 to 33, all this cluster of cells, they do have some variable number 2, 3, 6, 7, 7, 8, you know. So and the rest, which are false, 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 are probably don't have anything around them. So maybe this is working. I'm so excited about this. I'm so excited about this, so I can't wait to now figure out. All right, so let's now implement a rule where we decide based on the number of neighbors whether if the cell should give birth, should remain alive, or if it should be dead. Okay. Let's go back to the C# component, and then here all the way at the end, once we have computed all the neighbors, I'm just going to move this line of code at the very end and say, well, here, let's say I'm going to compute the new state. Okay, so previous state was cell array blah blah blah. Okay, now we need to compute the new state. New state, and we're going to initialize it to false, for example, and then we're going to write two conditionals. If the previous state was death, then we only have to check if the cell will survive, and if the previous state is alive, then we have to check if it remains alive or if it dies otherwise. Okay, so what that means is that I'm going to say if previous state was false, which means the cell was dead, then let me check if, given the number of current neighbors, if it should become alive. All right, so what I'm going to do is how do I know what is the birth rule? The birth rule is like all the integers that are here in my birth rule list. So what I can say is I can go over each one of the values that I'm plugging in here on the birth rule, and I go over all of them, and if any of them matches how many neighbors this cell has, then I should change new state to becoming true. All right, so I'm going to say for each integer b in birth rule, all right, and I'm going to say if b equals to how many alive neighbors are there, then I should change new state and make it true. All right, that's a very simple rule. This is going to be if cell was dead. All right, otherwise, if the cell was alive, so if cell was alive, then what we need to do is we need to check for survival. All right, so what that means is that we need to check if the previous state was true, we need to check how many neighbors are, and if the number of neighbors matches any of the survival rule numbers here, so 2 or 3, then new state should be true. Okay? Okay, so I'm going to do that again for each integer s in survival rule, for each integer in this list. If that integer equals how many neighbors do we have right now, then new state should be changed to true. you can see that by default, the new state is going to be false. We only need to check if we need to change that to becoming true. All right? And one thing that I would like to add, we don't really need this. This is just like a tiny bit of optimization. But something that we can say is here, we can add a break statement, which means that if we found that we had one match with each one of these, we don't need to keep checking the rest of the list, because checking the rest of the list is redundant because we already found one match. So by adding here a break statement, what we do is we stop the for each loop from continuing and we move on to whatever comes next. All right. So same goes here. This would be very good if we had like a long list of checks, but otherwise it's just good practice, at least to know it. Okay. Good. So what that means is that now that we know the new state of what we want, we can go back to new cells and we can store this new situation. We can store it exactly where it should go in the rows and the columns. So let me do that. So store new state in new array. All right, so I'm going to do that by going to new cells and J, comma Y, because it's column and row order. And here we're going to write new state, semicolon. Okay. I'm going to run this code. I don't get any errors. Are you guys ready for this? Are you guys ready for this? Let's try if we can get one iteration going. So we're going to say, instead of outputting the cell array, we're going to output the new cells array. So this new iteration that we just created. What? Did you see how this area here changed from true to false? Let me actually work with that a little bit. Previous state, so what we just got, no, previous and new iteration, new iteration, all right. And then in previous, I'm going to write cells array, and in new iteration, I'm going to write new cells. Okay, so this is going to be, what did I have here? Cell array. Okay, cell array, you can see, and let's compare things. So we have this here. I'm going to plug in the new iteration and the number of neighbors, and you can see that from this cluster that we have here, you can see that they were all contiguous, and now it kind of like only the ones that are on the tips of the row survive, and all the ones in the center die, which is kind of how this works. So let's visualize that. So what I'm going to do is I'm going to take all these points here, the ones that are inside. I'm going to flatten those points. All right, and then I'm going to use the new iteration as a calling pattern to pattern these ones here. And I hope, whoop, all right. And does this make any sense? Let's compare this with what we had with the ones that were contained. So let me check that. So that was here. And the pattern was this one. Was it this one? No. What was it? Okay, so this. Are there any points? 78 locally defined values. Why are these guys not rendering? From integer to, oh no, because I need to call this guys here. All right. So does this make any sense? Let's take a look at that. It looks like we had these guys. All right. This is what we had before. And this is what we have now. So what we had before was this. So this cell has 3 neighbors, it remains. And these two pop up here, this pop up here, this pop up here. That doesn't really make a lot of sense. This one should not be popping here because it only has 1 neighbor here. And this one doesn't have a neighbor. This one only has 1 neighbor, so it doesn't really make a lot of sense. And these ones here in the boundary, they should remain. So I think we're probably doing something wrong here. So let me take a look at what's going on, and then I will get back to you. Yes, it took us some time, but we found the problem. If you want to see what happened and how we found the problem, there will be a link on the video to the original recording, so you can just check it out. But basically, there were 2 problems. One was that I made a mistake, and as I discussed when we were showing the, as I discussed before, when we were showing this, I showed that the birth rate should be 3 for the original Conway Game of Life, and instead of that, I wrote the number 2 here. So we need to change this to number 3. And the other thing that I had incorrect was that during copy pasting, I made a huge mess here at the very end where it says bottom right, and I had like all this like nasty code that was like kind of like I had done something like there was something like this going on. So you just need to go back to bottom right and clean up the end of this and remove everything that was all the extra bad code that was there. But now we have something that makes more sense because you see these are the original ones, and the new ones that are popping out are these ones with 3 neighbors, this one with 3 neighbors, this one with these 3 neighbors, this one with these 3 neighbors, this one with 3 neighbors, but not this one that has 4. And here, this one is popping up, this one is popping up, this one, and this one is staying. You can see that it's staying alive because it has 3 neighbors only. Okay, so it looks like this is working correctly. Great, so it's working, but it's only working for 1 state. So it's only doing this computation just once, right? What we would want to do is we would want to control how many of these iterations are going to happen. So in order to do that, I'm just going to go ahead and like add another parameter to the component where it says how many iterations I want to go through. Rosa, survival rate. I'm going to add another parameter here called iterations, which is going to be of the type integer. And I'm going to plug in here a slider. I'm going to move things out of here a little bit. It's a little busy. I'm going to add a slider that I'm going to set to the value of 1. And the only thing that I'm going to do is here in where I have my code, where I say, let's calculate how many, let's calculate what are the new cells, okay? What I'm going to do is this double for loop where I check every, can I say this? What I check what I check in every, when I'm checking the float array every iteration, what I'm going to do is I'm going to wrap it inside of a for loop so that we do this operation multiple times, okay, over several iterations. Now, what I'm going to do is I'm going to wrap this here, and I'm going to say for int k equals 0, k has to be less than iterations, and k plus plus, and then I'm going to add a closing curly bracket all the way down here. Okay, so let's take a look at this. If I run this code, it is not going to work because first, now I only have 1 iteration, but also because if I crank it up, you can see that nothing is really changing, and it's not changing because if you look at the code carefully, you can see that when I take values for the calculations, what I'm doing is I'm still always taking from cell array, and cell array is the array that had the original data that is coming into the component. Okay, so no matter how many iterations I do, I'm always computing over the initial data. I'm not computing over the last iteration of cell calculations that I made. So we need to change a little bit of the code here. And what I'm going to do is I'm going to say, I'm going to first say this is going to be the new cells are going to start as a copy of the original data that I had. So instead of creating a new empty array, I'm just going to copy the array, but it doesn't matter because I'm going to overwrite the data constantly. And then here, instead of looking, can I do this actually? No, I can't really do this. No, this is not a good way to do it. So what I can do is I can say new cells is going to be, okay, I'm going to pause here. Yes, so the way to do this is going to be easy. So what we're going to do is we're going to work a little bit with the arrays, and I'm going to make a couple changes here. So what I'm going to say first is I'm going to create an array that is going to be called previous cells that I'm going to initialize to a new Boolean array with columns and rows, and we already know this, all right? And I'm going to create also a new array that is going to be called new cells. And I need to create these two arrays because like every iteration, I will need to look at the previous cells that I generated. I will need to crunch some numbers and then create another array with the new state. And then for the next iteration, switch them. Whatever was new now becomes previous. And then I create I crunch more numbers and create a new state. So I'm going to keep switching back and forth between these two. Now, what's interesting is that at the beginning of each checking, I will need to switch those two states. So switch previous cells with new ones. So what I'm going to do here is I'm going to say whatever was new before now is going to be previous, and then I'm going to reset new cells to become something new. This is redundant, we don't really need this, but it's just good practice, just so that we know mentally, okay? And something that I would like to do as well is I would like to change here what I say new cells. New cells are basically what just came from the component, because we need when we run this for the first time, we need something here to become the previous state of our calculation. Okay, so we're going to do this here, and we also need to change something, and we need to change that when we read from top left, top right, etc., instead of reading from the cell array, we need to read from the array where we're keeping the previous state of our cells. So this is this one here. So cell array, blah, 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 another one, and another one. Okay, and here, by the end of the for loop, we set the value of what you just calculated into the new cells array. So that makes total sense to me. I'm going to run this code, and it looks like it runs okay. And if we go to 0, this is great. We didn't perform any calculation, so we still have the original state. But as we crank up, we go 1, 2 iterations, 3 iterations, 4 iterations, 5 iterations. This is really cool. This is starting to look interesting. All right. So let me just work a little bit. Take this. Let me make this a little bit more visual, if possible. Let me take the actual rectangles, the outlines of the cells, and yeah, and let me just that's fine. So we can take these guys here, okay? And what I'm going to do is, I was calculating it with the points of the grid, so with the corners of the grid. Why don't we just do this with the actual rectangles, okay? So let me switch everything to rectangles. I'm going to create these boxes here, and I'm going to just plug everything in here. And this is not working anymore, so I'm going to calculate the center of those of that polygon. So I'm going to do that by using the area component that calculates centers of things. That's going to be the points that I want to use here. Okay, and I'm going to have to change this. I'm going to plug in here because now it's not that is not corner points. It's the actual rectangles. Now it's different, you know. So now you can see that we actually do have cells. And as I do this, maybe we want to create planar surface, boundary surfaces, so that it's like, yep. And now let's iterate this. 0, 1, 2. Boop, 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 boop. Okay, how is that looking? It's looking cool, huh? Let me crank this. Let me crank this up a little bit. So, okay, and then, boop, 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 boop. Da, 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 da. And then we can now, I like how it's kind of sticking to the original. I find it strange that it's not getting outside of that original, but there's, but maybe that's how it is given this initial condition. I don't know. Well, there's definitely an error here because here this 3 should become this 3 here. This 1, this 2 should not pop up. So something is not working. Okay, but we can take a look at this sometime later. All right. So what are we going to do next? Let me take a look at that error and see if we can fix it. Yes, we found the problem. It took some time, but we did. And again, it was due to like making these things real quick and not caring about things that we were changing. So it turns out that I forgot that all the way here in the for loop, when I was going over and over, I always kept looking at the previous state from the original cell array. But now that I'm using these two arrays to keep track of previous states and initial and new states, this should be coming from the previous cells array. All right. And now that we have this, I want to show you while debugging, I created an array of integers that displays how many neighbors each of the cells has. And we can see that now it is working well. So for you can see that the elements that are popping up are the ones that have 3 neighbors, and also the ones that are remaining have 3 neighbors as well. But if I keep going, for example, iteration number 2, you can see that cells with 2 neighbors remain, cells with 3 neighbors pop up, but nobody else does. So I'm going to go to iteration 3, and you can see how cells with 2 and 3 neighbors remain, but cells with 3 neighbors pop up. So I think things are working right now. All right. Yay! Okay, we got it. It's working great. Now, one thing that I don't like about this is that we have to manually iterate with this slider, which might be okay for certain situations, but it's not a great thing to do. And also, if we were to crank this up to, for example, let me save this file first. If we were to crank this up to, for example, 100, it would take some, you see how it took some time to calculate, because it actually has to go through all the iterations before it reaches 100, no matter if before we were at, for example, 99. It doesn't matter. Oh, this is looking good. What I'm going to do now is I'm going to change the code that we have written, so that instead of having a for loop that does all the iterations, we're going to have a persistent state. So we're going to calculate every time just one iteration, but we're going to implement a rule where we're going to tick the component every like 100 milliseconds to perform one extra calculation and have this evolve autonomously over time. Okay. That's going to need a couple changes, but it's going to be super cool. Yes, the way we're going to do this is we're going to use a technique in C# scripting components, which is that we're going to create persistent data. What do I mean by that? Whenever I create a C# scripting component, you can see that the component, all the code that I write, the code that makes things actually, is inside of this private void function that extends all the way until the end of the component. This is basically a function that contains the solver, what we're trying to do with this component. The problem is that due to the rules of variable scoping, what happens is that any data that we create inside of this function is going to expire, is going to stop existing once the function finishes executing, all right? We can still output some of that data by doing this technique. So this is where we output our data, but that only outputs the data. That doesn't keep anything in memory within this component. Everything refreshes. So what I would like to do is I would like to figure out a way to keep some data in the memory of this component so that next time that I run the component, I can access that older data, work with it as part of what I'm doing, and then use it to export or to output more information from this component. This is this is called creating persistent data in the component. And the way you do that is by adding the data that you want to be persistent all the way at the end of the C# scripting component. Here, where it says custom additional code. Here is an area where you can create persistent variables, and these variables will keep their value over instances of this component running over and over again. So no matter how many times I update this component, it will always maintain this data. So for example, one trick that I can show you guys is, let's keep track of how many times this component has been updated. Update count. So I can create a variable outside here called update count. And then here during the outputs, I can say, I'm going to up this value by 1 unit, and I'm going to output it here on an output that I'm going to create right now. So here I'm going to say B. Okay, and you can see how B right now has the value of 1 because this component has been updated, has been doing calculations once. And then the interesting thing is that now if I change any of the inputs, you see how the component calculates again, refreshes, and if as soon as I go up or down or anytime I perform any calculation, this component is adding 1 unit to this. And it doesn't matter, even if I remove this, it still gives me another update and another update. So just any single time, any single component, any single input of the component has changed, I refreshed the value of update. What I'm doing with this is I'm creating persistent data that then I can use across the life of the component beyond the changes that are coming from the input. So why would I want to do this? I want to do this because since I am always working with two states, the previous state of the analysis and the new state of the evolution, I want to be able to keep the previous state as persistent data, so that the next time that I calculate, I fetch that data, I crunch the numbers, and I output the values. So let me do that right now. So what we're going to do is I'm going to remove these iterations because I don't need this anymore. And what I'm going to do is I'm going to say, well, before here I had a for loop where I had how many times I wanted to calculate. We're not going to do that anymore. I'm going to remove this for loop here. Okay, I'm going to remove this that I just created as well. And then what I'm going to do is that previous cells which is the array that kept where I was before, I want to use that. I want to use that as persistent data. So I want to keep how many cells were in my previous iteration. I want to keep that as a value across the life of this component. So I'm going to move this here, down here. I'm going to remove this because I don't have this anymore. And then what I'm going to say here is at the beginning of the component, I'm going to say initialize calculations. So if reset equals true, then what I want to do is I want to take previous cells and make it equal to the value that is coming. Or sorry, I want I can turn I can actually just copy and paste this in here, and then say I'm going to initialize previous cells to be this array, and I'm going to take what's coming off as data, and I'm going to put it in here so that I initialize the previous cells array. And I don't need this anymore. Here, I don't need this anymore. I don't need this anymore either. And then new cells is going to be a new array. Blah, 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 blah. Previous states, I'm taking it from previous cells. That is correct. New cells becomes the new state. And I need to make sure that after I output, in previous cells, I store the value of new cells for the next iteration. Store new cells for next iteration. All right, let's see what mess have I done. The name cell array does not exist. So line 74. Where is this 74? It's previous cells. You see, copy pasting. Then the name new cells does not exist. Line 87. Well, because I have not declared this. You're right. So this should be a Boolean like this. Okay. And then 103 previous cells. Okay, this is previous cells is not set to an instance of an object. Okay, so I need to reset. Okay, and as I do reset, I let this go. You can see that now I get, and now as I did let this go, I have calculated one iteration. So that was here, that is here. Yep, so it looks like the data is now persistent, and I can calculate things across time. But then how do I actually make this evolve? So how do I make more iterations, more calculations? I need to make this component update more. So I need to force it to calculate more times. So there are two ways that I can do that. One is I can use a ticker technique. So basically I can just add an output, whatever. I can just call this ticker. It doesn't really matter. And it doesn't matter what it is, because the only thing that this is the only thing that this is useful for is to force a change in the component. So for example, let's see. I click this to true so that I reset. I set this to false. It updates once. And now every time I change anything on the inputs, you can see that this calculates. What I'm doing here is I'm basically, by changing one of the inputs of the component knows that it needs to re-update itself, whether if it's using this input or not. It doesn't really matter. Okay, so that is one technique, but we're still using this like crappy button kind of interaction, which I don't like. So I'm just going to remove that. And what I'm going to do is the other technique, which is the coolest one, which is that I'm going to use a timer. A timer is a component that basically does what I just described, but under the hood. A timer is a component that forces another component to update via ticking it um, um, at continuous intervals of time. So if I place a timer here and I plug it in here, you can see that this timer every 1 second is going to tell this component, can you please update? Can you please update? And then you can see that now we're getting these updates, and I can actually change the interval to 100 milliseconds, for example, and my definition is super slow for some reason. I don't know what's going on here. It shouldn't be this slow. But yeah, game of life. Awesome. So as you can see, I can turn on and off. Resetting this, and I can plug in a timer so that we get the evolution and we get one iteration every 100 milliseconds. I can restart this again by toggling this. I can, for example, I can reshape this curve, make it bigger, for example. Let's see how that looks. Boop. And let's see. Oh, that evolves terribly. That was so not cathartic. Okay, so let's take a look at this instead. Okay, so I don't like that. Let's go back to where we were. Okay. Okay. Turns out that we had a really nice curve, apparently, you know? So yes, so now it's working and all these cells are evolving over time. So that's great. So it took me a little bit to finish this one part with all the back and forth. As you can see, I didn't really prepare much. Whoa, that pattern is looking really cool. So it took me like a little bit of time to do this first part where I did some simplifications. Wait, let me check. Oh, cool. We're wrapping. So it took me like a little bit of time. I'm going to make this faster by cleaning up nothing that things that I don't need for rendering. And so it took me a little bit. So this is going to be the end of part 1, where I'm going to where I used a simplification of the data into the component in order to make things a bit faster, which wasn't that fast anyway. But what I'm going to do is I'm going to record another video where instead of simplifying the list and flattening it, oh, look, a glider. It's going. That guy is going to keep going and going diagonal. Let's crank this up. Let's make this faster. It's going to keep going and going. Oh, you see the tiny guy? Come on. So yeah, so I'm going to, and it's going to wrap around, and now it's going to hit this guy, and they're both going to blow up. Come on, come on. Nice. That was cool. So maybe we get another glider spinning out. So yeah, so I'm going to, sorry, I got distracted. This is really cool. So I'm going to record now another video, part 2, where I take the list of data as a data tree. I work with that data tree and I output a data tree with the same structure so that we can use this component that we just created for anything that gives me a 2-dimensional grid of objects in tree form. Okay, so thanks a lot for holding on, and yeah, and see you on the next video.